So yeah, you can start now.
Okay, let me share my screen. Back up again. Entire screen. Should we start from the start?
If
What?
tired already, you can start from the start, but don't really spend much time. Or yeah, you can just refresh from the start.
Okay, okay. I will just like quickly go over it.
Okay.
So, hello everyone. This is our third session, and today we'll be talking about model training and testing. So, previously, what we did was that we saw what AI was, what was the difference between machine learning and deep learning. Then, right after that, we tackled the different applications that is on computer vision, NLP, and right after that, we talked about the data, that is data process, that data ingestion, data processing, preparation, and then validation, and the importance of its high quality. So the ML pipeline is once again as the following. So we start by preparing our data, then we train our model, evaluate our model, then deploy it, and then maintain it, right? This is the cycle. So in data processing, usually after cleaning the data, performance of feature engineering, one of the things we usually do before feeding it to the models is that we split the data. So why do we split the data? Let's take an example of how we human beings learn. So usually, when we are being taught a certain material, let's say, for example, we have a professor teaching us maths. Usually what they do is that they expose the course, right? They start explaining the course, the different examples, and then when they're giving us a different example inside the class, that's what we will call our training data. So this is what the teacher is teaching us. And then inside the class, usually the professor will give us some exercises perhaps to do at home. And right after that, the professor would correct these exercises with us. So we can think of this as the validation data. Then later on, the professor will give us an exam and then give us a mark that is a passing mark or failing mark. This is what we can call as the test data. So what we do is that after ingesting the data, we split it into normally three different kind of data sets. That is the sets: the training, the validation, and the test. So the training and the validation aim to teach the model about our task. Meanwhile, the test data aims to evaluate the performance of the model on that specific task. So right after splitting our data, what we do is that we feed it to the model. So when it comes to the model, depending on the task and the domain, we will choose some set of models to try and compare against. For every model, we usually have a set of parameters that can be improved. That is what we call tuning or hyperparameter tuning. Right after that, we would evaluate the performance of the model on the specific task using the test data set. That's usually when we will be calculating performance measures like accuracy, precision, recall, also depending on the task. So one of the things we do usually when splitting the data, instead of just using the train, validation, and test set, there is a very interesting way to do it as well called k-fold cross-validation. So k-fold cross-validation refers to the fact where we have it's still one data, but we will be having different iterations of the data set. The k is just the number. You might do threefold, fivefold, tenfold. You choose however you deem fit. But usually in literature, what they do is that when we have few data, they split it into tenfold cross-validation. Meanwhile, when we have enough data, they will split it into the fivefold cross-validation. But for example, for my own case, usually when I do not have enough computational power, I usually, for example, only split it into fivefold cross-validation. Because yes, splitting it takes a lot of computation power because you will be training for every iteration. So what is it exactly? So we have our full training data, and then in that full training data, we will be taking a certain set. Let's say, for example, the first 10% will be our test for the first iteration, and then the rest will be the train. The second one, for example, we will train we will get, for example, right after the first test percent, we will take the second test percent at the test, and then all of it will be the remaining training data. So that's it. It's actually the same data, but we're kind of like changing the position or changing the test set, like changing it from the same data. And so for example, here we have 5 iterations. So we get for every of these iterations on every fold, we actually get the performance for every one of these. So let's say, for example, we're calculating accuracy. We will get accuracy for the first fold, second fold, third fold, fourth fold, and fifth fold. Then for the general performance of the model, we will get the average. And that's how we know how the model is performing. So why are we doing this? So the main reason is that we can ensure that the model's performance is stable even if we change, let's call it, the distribution of the data. That is, I don't know, perhaps like sometimes, usually when we spread the data into train, validation, tests, especially if it's static way, that is, we do not change what it sees, the model might get really good at the test and validation and then be really bad at the test. So what we ensure that it has enough variability. For the learning types, so usually before, what we did was that we get the model, we feed it the data, then we train it. The problem is that to train models, especially like ResNet 50, I mean, ResNet 52 is still very good. Inception ResNet 50 V2, Inception V2, these huge models, we need enough data. And data, like for example, Google trained them using 10,000 to 20,000 images, for example. That's a lot of data that not everyone has access to. And if we want to make AI accessible, we needed to find ways to reduce this load, right? And remember, if we have lots of data, it means we need lots of computational power. And computational power is not only expensive, it's also harmful to the environment. So the more huge models we train, the more carbon dioxide we actually emit. So we need to reduce it from any kind of aspect. That's why we use what we call transfer learning. So what is transfer learning? So usually, let's say, for example, Google goes around, takes the 20,000 images, train a model to differentiate between, for example, in this example here, between a knoll or a hawk, or you can say between a cat and a dog, right? It can be anything. Then, right after the Google finishes, it will save this model's parameters along with its weights. Then the users, as we will be taking these weights and these, all this saved model, and we will be reusing it on our specific data. So let's say they were trained to distinguish between cats and dogs, and we want to train it to distinguish between a butterfly and I don't know, and a tiger. I'm just obviously exaggerating. By the way, when the pre-trained models are trained, they usually train on different tasks. That is, they weren't actually trained on to differentiate between cats and dogs. They were trained to differentiate between many, many different tasks. That is, I don't know, cats, all the animals out there in the jungle, they were trained to distinguish between them. And so when we're leveraging this model for our case, we're taking, usually this model has already learned about all the available features of animals. So we're just reusing it in a certain way. This is what we call transferable learning. This is simple, basic transfer learning. Now, let's say, for example, we actually want to train the model on something completely different. I don't know. We want to train it to differentiate between a mug and a book. And the mug and the book, they were not part of the training data, perhaps. So what are we going to do? We're going to retake the same model that Google trained, and then we will fine-tune it on our specific data. That is, we're going to freeze, for example, the first layers that have learned edges, features. So they learned very simple, peculiar features like edges, corners, just the simple basic ones that are approximately available for any kind of object or living being, right? And then we will fine-tune the last layers that are specific to the specific task. That is, if it was learning the differences between the different animals in the animal kingdom, we will be removing the features only available for the animal kingdom and then training our model to differentiate between the mug and the book. This is why we usually would use fine-tuning. Obviously, this is an expensive task as well, so we need to be very mindful when to use it and how to use it. So usually, the number of layers we can fine-tune depends on the data set, the number of instances we have on the data, the computational power, and also how close is our data to the data that the model has been trained on. So for example, if Google trained it on any kind of type of images out there available on the net, we wouldn't really need much fine tuning if we're testing it on natural images, right? Any kind of image out there. But if, for example, Google has trained it on natural images, but then we wanna, deploy our model for a medical task. In this case, we might have to fine tune more layers. That is perhaps the last two layers of the model instead of only the last layer. So for example, if we take this convolutional neural networks in here, we have the input image and we have the first convolution layer number one, the second convolution layer, and then we stack all of these and then we move to the fully connected layer. The feature extraction part of the model is this convolution layer number one and convolution layer number two. So this is, for example, what we might want to fine tune. And like, for example, we might want to fine tune just the convolution layer number two so that it learns from our own images. And as you can see here, for the convolution layer number one, it is only looking at very small edge, at basic everywhere available edges. But in the second layer, it has started to learn specific edges just for the number 7. So this is why we usually freeze the first convolutional layer, for example, or the first few layers, and then unfreeze the later part of the layers before the fully connected layer to learn on our specific data when we're trying to perform fine-tuning. So for the metrics, as we have seen in the first week, we have things like confusion matrix, recall, precision, accuracy, F1 score, and MCC. So confusion matrix is an extremely valuable metric because it provides us an idea around the false positives, false negatives, true positives, and then true negatives. Practically, it tells us how the model is doing, how bad and how good it is doing at the same time, and where it is failing. For accuracy, only gives us a general idea of how the model is performing. Meanwhile, precision only tells us when the model is right. And then recall might tell us when the model is, precisely right by actually kind of like detecting the actual class that we're trying to detect. And then F1 score and MCC. F1 score is used for mostly when we have a huge class imbalance. So it is very good because it actually penalizes recall and precision. While meanwhile for MCC, or Matthew's correlation coefficient, it is actually used when we have different classes. That is, when we're performing the multi-class classification, this is the best metrics to use to account for it. So there is also something else that we use, and that is called ROC curve. So the ROC curve, or AUC, area under the curve, are highly used also when we have a huge class imbalance because they account for the false positive rate and true positive rate. So what is the true positive rate? So the true positive rate is the true positive divided by the true positive plus the false negative. What does it mean? So it's the ratio of correctly predicted positive instances out of all the positive samples. For example, if the model is tasked to identify the fraudulent transaction, then the true positive rate is defined as the proportion of correctly predicted fraudulent transactions among all the fraudulent transactions. So only the correct ones, that's what the true positive rate accounts for. Meanwhile, the false positive rate accounts for the fraudulent transactions, for the fraudulent alerts out of all the legitimate transactions. So this is why they are good to plot, because they kind of like complement each other and gives us a better view of when the model fails and when the model is right. So the more we are closer to the left upper one, the better the model is. The more we are closer to the right lower one, the worse the model is. A perfect classifier will try as much as possible to kind of like a stick to this upper left one, right? And then a random classifier, that is, you might as well call out someone who can gamble for you. That's a random classifier. That means it 50% it is right, 50% of the time it is wrong. So this is, for example, this is an example. So in here, we have the true health condition. Let's call it the actual label, the real one. And then we have the diagnosis. That is the prediction of the model. So the true condition here is has disease or healthy. So the model is trying to predict if someone has a certain disease or if that person is healthy. So for this one here, so if someone has a disease, this is the true label, and then they are diagnosed with the fact that they have that disease. This is what we call the true positive for this case. If someone is healthy but then is, taken as has a certain disease, that is the false positive. If someone has a disease but is diagnosed as healthy by the model, then this is a false negative. This means this is a false alert. But if someone is healthy and then they are classified as healthy, that is what we call the true negative. That is, they do not have the case that we're looking for, they do not have the disease, and indeed the model predicted they did not have the disease. So sensitivity is or as seen here, the true positive rate, sensitivity, is true positive over the has disease, right? And then specificity, the false negative, a part of the false negative rate metric is the true negative over the healthy. So if we want, so the true negative rate, the false positive rate, is 1 minus specificity. So sensitivity and then 1 minus specificity account for the true positive rate and the false positive rate. So as we can see here, if you remember, the closer we are to this upper left one, the better the model is. So this is why they call it very good biomarker one. Meanwhile, for the one that is closer to the left, down left one, it is a very poor model, a very bad one, because it is closer to the diagonal, which is obviously the 50% 50% of the time the model fails, 50% of the time the model is right, which is practically a gambler. That's it from our side. If you have any questions, please feel free to send them my way. Thank you. What did you think? I finished. Victor? Victor, are you still here?
Okay, so yeah, I'm here. I was in this session. Um, okay. So can you talk about the part of? I have a question. Can you talk about the part of transfer learning?
Yes, yes. What is the question?
Um, uh, you explained transfer learning, but I want you to talk about it, given like maybe I have a model already that is working, let's say for object detection, and I want to sort of like add transfer learning to it, maybe to learn new weights.
You're trying to do what? Sorry, I can't hear well. What are you trying to do?
Okay, I said, let's say I have a new model
Yes.
and sorry, a model that does vehicle detection, and I want to and I want to add new weights to it, new layers, so that maybe it will be able to identify new classes of things. Can I use transfer learning, or where can transfer learning fit in very nicely?
Yes, you can use transfer learning for any task you have whenever you need to use it. So, for example, so practically there is two things. You can either do transfer learning, that is use someone else's model, right? Or with their weights and then train some more on your data, or directly use it to do the detection, right? No training. Or you can train on your data from the start. That is, you're not leveraging other people's model or weight, but directly training, using your own architecture or just a basic, architecture. But like there is no weights already available. The model hasn't been instantiated. The model hasn't learned something previously. It's like a newborn with the young adult or something like that, right? That's kind of like the difference. A newborn doesn't have no idea what's happening in the world. It is still learning. That's what we call training from scratch. But transfer learning is like you're calling a young adult, right? Or any teenager, and then having them learn the task.
Okay, okay. Thank you for the explanation.
You're welcome.
So, thank you for the explanation. So the questions that we have, I'll send it to you maybe through the comments on the YouTube channel or
Yeah,
any other thing.
feel free to do so.
Okay, thank you. So at the meantime, I'm going to end the call and share it on YouTube so
All
they
right.
can watch it.
Thank you. Have a
Thank you.
nice day. See you next week.
Thank you. Yeah, see you soon.